Our overview of portfolio seismic risk assessment. This is presented for ASTM Subcommittee WK55885, Seismic Risk Assessment of Real Estate Portfolios, and it was prepared by William Graff and Yaji Lee. Here are the things we'll cover: introduction and background, terminology, seismic hazards and event sets, modeling uncertainties in ground shaking, loss estimation, mostly for buildings, although contents and BI may be included, loss aggregation for each earthquake simulation, stakeholder models, and using the lender loss model as the example, outputs, exceedance probability curves, risk deaggregations, recommendations for best practice, and bibliography and resources. Part 1 is introduction and background. So why do we do portfolio seismic risk assessment? What are the benefits? Owners and lenders and others need to know the total strategic risk, not just the site-by-site risks as provided by acquisition due diligence reports. Those are PML reports. And we want to identify the geographic concentrations of risk and other factors that contribute to large aggregate losses. The owners and lenders need to make better decisions for investment and sale and set better policies for acquisition due diligence. And then finally, to manage risks through strategies like geographic diversification, earthquake insurance, and seismic retrofit. So here's an example. An owner may ask, how much earthquake insurance should I buy? And there are several different approaches. One approach might be to use insurance-based catastrophe modeling without any engineering input, and that's represented by the red curve. And then if we go in and do improved modeling with engineering input for the buildings and for the sites, then some of the conservatism might be removed and the blue curve might be what results. And then if we're really looking for insured losses, the losses that would be paid by the insurer, we can put deductibles or other buffers in play, and we could be down to the green curve. So you can see that in terms of portfolio-wide loss amount, we get these curves are decreasing in terms of the loss amounts. And another aspect of these risk curves is the fact that you can examine them at any return period or any level of probability. So if the owner says, how much earthquake insurance should I buy? The answer does not have to be the largest amount that could be lost, which might be represented by point D, but we can put the engineering to work and the buffers to work, and we can look at a more reasonable return period, anything from 200 years to maybe 475 years, or whatever the owner's risk appetite dictates, and we can reduce the amounts that are purchased from D to C to B to A would represent the amount that the insurer would pay on a 475-year basis, and that might be an appropriate amount at which to seek coverage. Of course, there are other things that could enter in, things like demand surge and that sort of thing, and lender risks are a little bit different. But this is a good example of a question that may arise that would warrant good portfolio seismic risk assessment, and where the effort put into the study could reduce the cost of the earthquake insurance very significantly. So this slide shows a history of portfolio risk methods, starting with the 1970s and going till present. And we could rough out basically 4 different eras where at first risk management was a simple tracking of exposures and accumulations of exposures in various different zones dominated by particular faults. And then that progressed into deterministic catastrophe scenarios, where you might look at a San Andreas earthquake in Northern California, or a San Andreas earthquake in Southern California, or a Hayward earthquake, or a Newport Inglewood earthquake. Or you might look at another particular earthquake like Wasatch Front in the Salt Lake area. So, and then in the 90s with AIR and RMS and EQE, the large catastrophe modelers coming in with more sophisticated methods, risk curves, exceedance probability curves were developed, and those are produced for synthetic catalogs of earthquakes called event sets. And so the risk curve era is one that we're in at present. And then there are some even more sophisticated tools coming along that we call robust simulation, where they disclose more of the uncertainty and the variability in the models that are involved. So, of course, all of this has been aided by the developments in information technologies, starting with mainframes and then the IBM PC, and most recently cloud computing. And of course, the various different earthquakes have propelled advances as well, as have the development of the various different maps and products of the United States Geological Survey, starting in the 70s with the first probabilistic maps by Algermissen and Perkins, and more recently the work of the National Seismic Hazard Mapping Project under Frankel, and then more recently under Peterson. So all of these things have propelled the development of the tools that we're talking about today. Here's a backbone of the computational process, simplified for easy understanding. All of the computation proceeds earthquake by earthquake through a large inventory or catalog of earthquake simulations we call an event set. And then for each earthquake, we could take the hazards that are depicted for that earthquake at each site and calculate the losses at the site for building and contents, time element losses, other things. And then those are summed up across the site and then summed from site to site for over all of the sites. And we construct then the aggregate or portfolio-wide loss, and we allocate the loss to the various different users, to owners, to lenders, to insurers, to others who may have a stake in the losses. Those losses are then linked to a probability, an annual probability of occurrence or an annual frequency of occurrence, and then we proceed to the next earthquake. We repeat the process for all of the different earthquakes, and then we go and take that large list of earthquakes and probabilities and consequences and sort them from the most severe consequences down to the least severe consequences, and we construct risk curves considering uncertainties, we compute average annual losses, and we identify the sites and buildings that drive the losses. Next, we can discuss the terminology that's involved. First thing is portfolio. A portfolio is a geographically distributed set of facilities. Usually they're real estate properties or buildings. They may be other values at risk as well. So what we show here is a typical large portfolio that's distributed along the West Coast. It's in San Diego and Los Angeles and the Bay Area, with some additional assets in Nevada and the Reno area, as well as Portland and Seattle in the Pacific Northwest. And you can see that the picture is quite complex in terms of the number of earthquake faults that may affect the portfolio and the different exposure amounts that we have for each building. So it's not always intuitively obvious which are the clusters of assets that drive the risks and which ones you need to be most careful with. A little more terminology An event set, that's a set of earthquake simulations, each with a spatial distribution of ground shaking and an annual frequency of occurrence. And this entire set of earthquake simulations is intended to represent the complete ensemble of future earthquakes for the defined region. And it's used for the evaluation of earthquake damage to spatially distributed real estate properties. So next is stakeholder. That's one of the parties who may suffer damage, loss, or injury from an earthquake event. For example, an owner, lender, or insurer may have a stake in an earthquake loss. If the owner retains earthquake insurance, then the insurer is at risk for covered losses when an earthquake occurs and causes losses above deductible but below the limit of liability. If the owner defaults on a loan, then of course a lender may be involved through foreclosure. More terminology. Aggregate loss, that's the portfolio-wide loss for the particular stakeholder in question, and it's usually expressed in dollars from earthquake events. Ground-up loss, this is an insurance term. It's the total financial loss considered by an earthquake insurance policy prior to allocation through the application of deductibles and limit of liability. So it's all of the losses that would be paid by any party. The portions of the ground-up loss that are retained by the insured, that's usually the owner, are the losses below deductible and loss in excess of the limit of liability. The portion that's paid by the insurer, that we can also call the direct loss or the gross insurer loss, is the loss above deductible but below the limit of liability. Also, we speak of expected loss, and by that we mean that's the mean value of loss in dollars from a statistical distribution of loss that considers the uncertainties. This can apply to a single building or to a portfolio, and in which case we also refer to it as aggregate loss. Probable loss, that's the earthquake loss to the building or portfolio that has a specified probability of being exceeded in a given time period, or an earthquake loss that has a specified return period for exceedance. And this is found through detailed analysis that includes the consideration of uncertainty. Lender loss. The financial risk to a lender from earthquake damage to a property that secures a mortgage, should the owner choose to default on the mortgage. An owner may elect to default on a loan if the cost to make the earthquake repairs exceeds the owner's equity in the property. And equity is found typically as current market value minus the mortgage balance. So upon default, the lender may choose to foreclose on the property, and then they would need to make the necessary repairs and sell the property to try to recover their mortgage balance. So the lender's loss might look like this. Lender loss equal to the sum of the mortgage balance and repair cost, and then minus the recovery, the market value, upon sale. Alternatively, the lender may elect to maintain ownership of the property. Average annual loss, or AAL, that's the loss per annum due to earthquake hazards, calculated from the probabilistic loss distribution that considers all of the different events. The expected annual loss, or average annual loss, it's the expectation of the probability distribution of loss per annum, and it can be calculated roughly as the frequency weighted average of loss due to all possible hazard events. And you see down below AAL equal to the sum of the loss sub I times the frequency sub I for all events sub I. Next we talk about risk curves or exceedance probability curves. These are defined as plot of the severity of loss or other consequence as a function of annual exceedance probability, or average return period. So this is a continuous form of probable loss, such as we encountered in ASTM E2026. And you see below a plot of exceedance probability, where we have the annual probability of exceedance on the y-axis and portfolio-wide loss amount on the x-axis, and the blue curve then tells you what value of loss has a particular annual probability of exceedance. Another way of representing the same information is with the risk curve shown below, where we plot portfolio-wide loss as the y-axis and average return interval as an x-axis, and in order to cover the span of years that we'd like to, we typically make the return interval a logarithmic axis. So then another thing that can be done with these risk curves or exceedance probability curves is to show multiple cases on the same plot for comparison purposes. And here we compare the ground-up losses for all regions with the ground-up loss for Oregon sites. So this may be a small part of the portfolio, and it shows how much of the risk is attributable to the exposures in Oregon. Next, we'll move on to site hazards and event sets. So the hazards that are in play in portfolio seismic risk assessment are typically ground shaking and liquefaction effects. And the liquefaction effects that we can model are usually limited to the damage from differential settlement on flat sites. Lateral spreading, lurching, etc., those are much more difficult to model in both their occurrence and their consequence to the building. Less important in portfolio seismic risk assessment are surface fault rupture and landslide. These may cause a lot of damage to individual buildings, but they're highly localized and typically do not contribute to high portfolio-wide losses, at least in portfolios where we have a large number of sites. So, in the catastrophe models that are used in earthquake insurance, such as those that are provided by Risk Management Solutions, AIR Worldwide, CoreLogic, Impact Forecasting, ImageCat, etc., the losses are computed for an event set. That's that large synthetic catalog of earthquake simulations, and that's used to reasonably sample all the future earthquakes based on our current understanding of the seismic environment. And then the engineering service provider has the opportunity to improve the modeling by making sure that the site class is correct, and that affects the intensity of ground shaking, and that the liquefaction susceptibility is correct. And this information can be taken from site-specific documents, such as geotechnical reports, and then used to override data that would otherwise be drawn from more general digital maps. And then where liquefaction may be possible to occur, the foundation type becomes important, since deep foundations may have been provided to mitigate the effects of soil liquefaction. Now, in modeling seismic shaking hazards, the parts of the model can be divided as follows. There's typically a seismicity model that accounts for the magnitude, location, and annual frequency of occurrence of earthquakes, and then there's a ground motion model that takes the magnitude and location and shows the distribution spatially, geographically, of ground shaking, and it depends on ground motion models or ground motion prediction equations or attenuation relationships, as they're more commonly called. An important aspect of modeling the ground shaking hazards is also site amplification, where rock tends to be less amplifying, and softer soils are more amplifying. So there are models like the factors we find in ASCE 7 or the ASCE 41 or other documents that provide factors like F sub A and F sub V, or there are also VS30 terms within the ground motion models that can be used to address site amplification. And then with all of these different things, there's a degree of uncertainty. There are distributions of seismicity. There's uncertainty associated with ground motion models and site amplification. So managing all of these uncertainties and accounting for them within the loss model is an important activity. In modeling earthquake occurrence, we have to recognize that exactly when, where, and how severely the next earthquake will strike cannot be predicted precisely. The future is unknown. The occurrences, locations, and magnitudes must therefore be modeled using stochastic methods to account for the uncertainties. On the right, you see a plot of the explicit faults considered by the United States Geological Survey in the National Seismic Hazard Mapping Project. So what is a stochastic event set? It's a large set of earthquake simulations that systematically samples all the magnitude frequency distribution and then uses finite rupture locations to account for all the possible future earthquakes in a region. Each earthquake simulation attempts to accurately reproduce the geographic distribution of ground shaking and other hazards using the ground motion models and using site correction factors. Empirical ground motion models are used with specific fault parameters like depth, dip, style of faulting, etc., and a particular magnitude and a defined finite fault rupture. The ground shaking is adjusted then for site class and other effects, and the predicted shaking is given as a response spectrum. And that may be either a smooth shape or it may be a constructed shape based on PGA, short period, and long period spectral accelerations. The number of earthquake simulations required for a seismically active region can be very large. We may need to do hundreds of thousands of simulations or even millions of simulations for a portfolio that is spread across the western U.S. The de facto standard for the ground motion modeling is the United States Geological Survey's National Seismic Hazard Mapping Project, and the models there were produced originally in 1996 but have been updated every 6 years since, so in 2002, 2008, and 2014. The most recent incarnation of the USGS model uses the Uniform California Earthquake Fault Rupture Forecast version 3 or USERF 3 in California, and that stitches together information from seismology, geology, geodesy, that is to say GPS, and all of that and paleoseismology into a model of the earthquake ruptures that may occur in the future. And this is a highly complex model. So with fault models, deformation models, earthquake rate models, all of this, and then it involves a lot of complex logic trees. And one set of models is used in California, another set of models in other locations, and all this gets stitched together within the National Seismic Hazard Mapping Project. Another aspect of the USGS models is the use of these specific next generation of attenuation ground motion models. These are the NGA West 2 ground motion models that were specifically developed for use in the National Seismic Hazard Mapping Project. And here we see a couple of examples for magnitude 7 strike slip faults, and this is taken on a soft rock condition, and we compare the PGAs and spectral accelerations at 1 second for a number of different site to source distances, and we have a number of different ground motion models compared there. The Abrahamson, Sylvan, and Kamai model, the BSSA or Boer, Stewart, Sehan, and Atkinson model. We have Campbell and Bozornia, and Chu and Young, and Idris. So all of those look like they have a pretty close agreement for a typical magnitude 7 strike slip event on a soft rock site. As already mentioned, another important aspect of these event sets is the correction of ground shaking intensity for local site conditions, and that's typically done using digital maps like the one shown from Wills et al. From 2015. This shows VS30 conditions that vary across Los Angeles, used to assign the appropriate site class. Now, when using the major catastrophe models, the engineering service provider will want to do some verification, want to do some checking as to how closely the event set and the hazards used in the CAT model correspond to the United States Geological Survey's National Seismic Hazard Mapping Project and the published results from this de facto standard for seismic hazard in the United States. So, in doing that, any catastrophe modeler's event set can be used to construct hazard curves. That's to say, spectral acceleration versus return period. And then you can compare directly with the values published by the United States Geological Survey. A typical comparison might be made for PGA or for short period spectral acceleration or for the 1 second spectral acceleration, and you may want to compare over a range of return periods, something like maybe 72 years to maybe 1,000 years, and we may want to do it on a standard ground condition like the soft rock ground condition, intermediate between site class B and C. Any deviations in modeling from the United States Geological Survey de facto standard should be explained and justified. Now, there are cases where it may be appropriate to differ from the United States Geological Survey. For example, in situations not accounted for by the USGS model. That would be in cases where there's significant topographical irregularity or where there's very soft soils, site class E might be an example, or whether there's soil failures, site class F. Also, deep sedimentary basins might be a case where special attention would be needed or some additional steps, or where directivity or near fault effects are occurring. And in those cases, there may be some different things that would be needed to be done. But in the verification of an event set, what you'd like to see is for something like 475-year PGA, that the catastrophe modeler is able to reproduce pretty faithfully the USGS distribution of ground shaking. So here's some points to consider. The event set is produced by model vendors, and it's typically not modifiable by users. The particular events and their effects can be examined in more detail, so you can look at individual scenarios, but it's typically not modifiable. The site hazards, including the shaking effects related to VS30 and liquefaction effects, those things can be changed and improved by the engineering service provider. The area affected by maximum shaking is small, and as the intensity of shaking diminishes, greater and greater area is affected, and that's illustrated in the sample event shown below. As a result, portfolio losses typically include a few highly damaged sites and many other sites with lower levels of damage. But these add up and are important in contributing to the overall aggregate loss. So it's important to have a good picture of the distribution of ground shaking, and then the damage relationships need to be accurate for all levels of shaking. Now we move into the third section, modeling uncertainties in seismic hazards. Of course, there's a great deal of uncertainty in ground motion prediction equations and in the seismicity models, and then even in site correction and other things like that. Generally, we can discuss seismic hazard uncertainties as being of two types. One is the aleatory uncertainty, or the randomness, and the other is the epistemic or scientific uncertainty, which is related to the choice of the model or models that we use. So with the aleatory uncertainty or randomness, this is the true stochastic nature of the natural phenomenon that's not being addressed by the model in question. It has to be represented by an uncertainty distribution, and thankfully with portfolio seismic risk assessment we have the law of large numbers and the central limit theorem on our side. So as we get to larger and larger portfolios, the uncertainty contributed by aleatory elements becomes less and less. Now there is another form of uncertainty, and that is a scientific uncertainty or epistemic uncertainty that has to do with the lack of knowledge. So this has systematic effects on risk that add up from site to site to site, and so it has a very significant effect on portfolio seismic risk assessment. It's more difficult to quantify and manage, typically addressed using multiple models and a logic tree to try and span the scientific uncertainty that's represented by models at present. So here's an example of a ground shaking uncertainty distribution, a log normal uncertainty distribution from a ground motion model, and this is the BSSA model, and here we see for a magnitude 6.7 earthquake a distribution of PGAs, and it might have a mean or a mean value of about 0.46 or 0.47 G, and then plus or minus 1 sigma takes us down to about 0.3 G and up to about 0.9 G. So this is quite a wide range of uncertainty. This is plotted out for site class D. The uncertainties in ground motion models have two parts, and the parts affect portfolio-wide loss differently. The typical ground motion prediction equation, you have some parameter like PGA or spectral acceleration that is a logarithmic quantity that's a function of magnitude and distance, plus a couple of error terms. And the error terms or uncertainty contributors, one is called the between event or intra-event term. That is the systematic earthquake to earthquake difference that you'll find, where within any particular earthquake, ground motions may be higher at all sites than typical, and that would mean that the losses at those sites would be increased, and that those differences add up from site to site to site. So that's a significant effect on portfolio aggregate loss. And then there's a within event term or an intra-event term, which affects ground shaking as it varies from site to site within a particular earthquake. And then the ground motion may be higher and the loss may be higher at some locations, while at others the ground motion may be lower and the losses may be lower. So these sorts of effects tend to cancel out within large portfolios, and it's important to then keep track of these uncertainties separately so that we can understand and account for the effects on a portfolio-wide loss basis. Now, there is spatial correlation of the losses from the intra-event term. These sorts of things have been modeled by folks like Park or by Goda and Hong and this sort of thing. And the correlation coefficients are represented as functions of period and distance, so that when two sites are located close together and have buildings with similar periods, they tend to be more correlated in the ground shaking. And this sort of thing needs to be taken into account and tracked carefully in building portfolio risk curves. Here's an example from Goda and Hong of the correlation coefficients as a function of distance and period. And you can see that when we take into account the spatial correlation of ground motions, the answers can be quite different from uncorrelated ground motions. And here we see an example from Lee et al., 2016, where over 3 blocks of 18 steel and concrete buildings in San Francisco, that as you get to longer and longer return periods, as you take into account the spatial correlation within that limited distance, that it can cause significantly higher damage at long return periods. Next, we turn to loss estimation in buildings. We can distinguish 3 types of damage relationships: expert-based damage functions, as exemplified by ATC 13. Other examples include Wiggins and Steinbrugge. Then there are statistical and actuarially based damage relationships, such as the study of wood frame dwellings from Northridge earthquake claims, done by Rob Wesson et al., again published in Spectra 2004. There are also engineering damage models, and these are more closely physics-based, although they have heuristic elements, and HASIS is an example of that. Of course, adequate statistics upon which to base actuarially sound damage relationships are pretty rare. Fortunately, the expert-based empirical models and engineering damage models can be used when this good statistical data is not available, and each type of model has its own area of use and competency. Let's take a look a little bit at ATC 13. There are 40 different California building types, typically Zone 4 type buildings. They're engineering related classes, so they're similar to the types of building descriptions that we find in seismic design codes, and they're consensus expert opinion from engineers. And we show one of those damage relationships at right with the damage factor or the damage fraction as the y-axis, and here the demand parameter is modified Mercalli intensity. There's another type of damage relationship. It's almost a hybrid of engineering and empirical damage relationships. We call it code-oriented damage assessment, or CODA, since it's related to structural design codes in terms of the parameters that are used. Jerry Lee and I developed this back in 2007 and 2008, and it was published in the Spectra Journal in 2009. The x-axis is a demand to capacity ratio, where the demand is the spectral acceleration at the ground at the period of the structure, and the capacity is the product of the R factor and the seismic base shear CS. So with that as the demand to capacity ratio, then the y-axis is the damage factor, the repair cost divided by the replacement value. And you can take any kind of information that you have, be it from engineering models or empirical expert opinion type data or insurance statistical data, and plot it into this space and create damage relationships. We did an initial calibration to the ATC13 damage relationships, and this shows an example of a bearing shear wall, a low-rise structure, and the damage relationships here as a function of the base shear and R factors, and where the spectral acceleration at the building period is the input parameter. This makes it very easy to take engineering-based findings and use it to improve your damage estimation. Of course, there's HAZIS multi-hazard. This was developed by Charlie Kircher and a number of others through NIBS for FEMA in the 1990s. The vulnerability varies by model building type, by height, and by seismic design level, and then there's further adjustment that the engineer can do both in terms of the capacity parameters and the fragility parameters, and you can also adjust the value at risk between structural and non-structural components. The outputs are expected damage, downtime, and probability of collapse. You also get out the damage state probabilities. So that's HAZIS. HAZIS uses a demand curve, which is a modified response spectrum, and a capacity curve, which is something like a pushover, and where the demand meets the capacity, we find a solution, which is an approximation of a nonlinear solution, and it tells us a displacement that gets translated back into a drift, and it tells us an acceleration that gets translated into a floor acceleration. And then there are fragility models for the drift sensitive and acceleration sensitive components to get us to a damage estimate. Here's an example of the use of HAZIS for probabilistic portfolio risk assessment. These are the concrete coalition buildings that are so famous in LA. We took the inventory from Professor Anagnos from the Concrete Coalition, 1,454 buildings, and pulled them into our Seismic risk software. And then with an event set that's drawn from the 2008 USGS, we constructed expected loss for the portfolio, and the highest modeled loss was a magnitude 7.2 Puente Hills fault simulation, and you can see that the risk curves can be constructed in a probabilistic sense from HAZIS for the portfolio. Of course, HAZIS has its limitations. It comes from FEMA as a part of a GIS system, and then it computes expected losses only. It doesn't give you a full statistical loss distribution. It computes portfolio losses for individual scenarios like the shakeout scenario or like the Puente Hills scenario we just pointed out in the other thing, and then beta values, the beta uncertainty values need adjustment for ground motion and building performance uncertainties if you're going to use it in a probabilistic analysis and adapt it for insurance uses. Now a question comes up: can we use FEMA P58 and incremental dynamic analysis and some of the state-of-the-art methods used in performance-based earthquake engineering for portfolio seismic risk assessment? And the answer is not really. The models that are used in portfolio seismic risk assessment are spectrally based, whereas the FEMA P58 methods use nonlinear dynamic procedures. The models used in FEMA P58 require many times the computational effort as the empirical damage models we were talking about, or the HAZIS models, and the models require much more building specific and detailed information. So these models are much more applicable to new construction, but this information gap is a challenge for applying them to existing construction. One item that's important in the study of the various different forms of damage relationships that can be used, or the critical evaluation of these damage relationships, are the performance of the damage relationships at damage inception and damage saturation. Damage inception is important in estimates of average annual loss and hence relates to earthquake premiums. Damage inception is also important in setting the earthquake deductible. Damage saturation is important for damage estimates in areas of large faults with many existing buildings not designed for earthquakes. Here you can expect very high levels of damage from a significant portion of the portfolio, and so damage saturation is important, particularly in setting the limits of loss or the limits of liability in insurance. So we have these various different published relationships, ATC 13, this sort of thing, code-oriented damage assessment, the Steinbrugge, the Thiel-Zudi relationships, other types of relationships. These are typically used in our PML studies as relating to E2026. But then there are the proprietary relationships that are used in the insurance-related catastrophe models by AIR, by RMS, by CoreLogic, by impact forecasting. So in these damage relationships in insurance catastrophe models, these are proprietary and the damage relationships are not directly inspectable, and at present there's no direct way to calibrate the damage models to the results of engineering studies, that is to say things like PMLs or other kinds of engineering studies. The engineering damage relationships, however, the damage models that make direct use of engineering parameters like HASIS or CODA and that sort of thing, these do allow more direct inspection of the damage relationships, and they make it possible to calibrate to the results of engineering studies, that is to say PMLs or other things like that. One thing to note is that when we're estimating consequences, when we're estimating in particular dollar losses, the dollar loss is equal to a damage factor times the replacement value. So the values become very important. It's not just the damage relationships, but the values at risk are just as important, and errors in these exposure values then translate directly into errors in loss or errors in consequences. Now, question arises, how do we improve the loss estimates when we're using commercial catastrophe models? So if we're working with an insurance broker or an insurer and we're using the large cat models, many of them start with occupancy-based damage relationships. If the insurance brokers or others using the software don't know the structural classes, they rely upon occupancy-based damage, so they will start with occupancies like dwellings or office or parking, and then the damage relationships become more general and have higher levels of uncertainty than damage relationships that are directly related to the structural system that's used to resist earthquake forces. So, but then these damage models also have structural classes that can be used if the structural system is known. So one place where the engineering service provider can make an improvement in the modeling is by taking the buildings and assigning the actual structural class to each of the buildings, or at least to the important buildings within the portfolio. So, wood frame construction, steel moment frame, steel brace frame, this sort of thing, by designating the particular structural class. Then the software will use a more specific modeling that's more appropriate for the particular building, and then it will also leverage the other known attributes of location and age and stories to provide the estimate of damage for the buildings. And if you know the structural class, the commercial catastrophe models also accommodate the assignment of these secondary modifiers that help to refine damage prediction. They don't quite provide you with the calibration you might be looking for to the past engineering damage studies, but at least these secondary modifiers help to identify when serious deficiencies exist in the buildings that would cause you to have higher levels of damage. Things like a soft story, or a shape or configuration problem, torsional problem, this sort of thing. So in the loss estimation for buildings, the loss estimate is not just a single number. We need to have statistical distributions for the damage relationships, and the best candidates for these statistical distributions of damage for individual buildings are things like beta distributions and gamma distributions and log normal distributions. Some of those are illustrated in this slide. So how do we construct a risk curve? Let's start with the simplest, the portfolio expected loss curve. So starting with the list of earthquake simulations in our event set, each with an associated mean portfolio-wide loss and annual frequency of occurrence, we can sort the losses from maximum to minimum. The frequency of exceedance for the maximum loss modeled is equal to its frequency of occurrence. The frequency of exceedance for each remaining loss is equal to the sum of the frequencies of occurrence for all events with higher losses. Return period is found as 1 over f sub b, where f sub b is the frequency of exceedance. The plot below shows expected loss for the portfolio then as a continuous function of return period. It's something like SEL, but for all of the scenarios affecting the portfolio, and we can see the return period for any level of loss. This process can be followed for the losses from any stakeholder position: ground up, gross or insurer loss, lender loss, and owner's retained loss. Now, to get to the more complex and complete picture that's presented by probable loss, we have to take into account the uncertainty associated with each of the events or simulations in the event set. So for each earthquake in the event set, the losses and their uncertainty distributions are used, and we go through a binning process whereby we account for the event frequency of occurrence and the statistical distribution of loss, and then we construct the risk curve by accumulating the frequencies in the given bins. Next, we'll look at stakeholder models, and these help us to distribute the loss between owner, lender, insurer, and other stakeholder parties. Here is an example of lender loss model. So what we have here is we're plotting the value of the loss on the vertical axis and probability on the horizontal axis. The figure at right shows the earthquake loss for particular building, say, and it has a probability density function, and starting at the bottom at a zero loss and reaching some maximum value not exceeding the replacement value of the building. So that's the figure at right. The figure at left shows the various different stakeholders and their position from first dollar loss on up. So the first dollars lost are to the owner and help to erode their equity, and if the owner has earthquake insurance, then that acts like additional equity, and the potential lender losses don't begin until the losses exceed owner equity and owner retained earthquake insurance. So if we proceed from the lowest level of losses and bin the various different losses, then we can compute the expected loss to any of the different stakeholder parties. Now the stakeholder models, as you can see, may produce some interesting truncated distributions, and that presents challenges in terms of constructing the aggregates, and so the process of tracking and accounting for uncertainties is much more complex as we have these stakeholder models. So what are some of the outputs that we get from portfolio seismic risk assessment? Well, obviously we've been talking about the risk curves. So we get these risk curves. They may be loss versus return period or loss versus exceedance probability, and there are of course equivalent tables that would be a function of return period or a function of exceedance probability. We can do the risk curves for the whole portfolio, or we can look at the risks region by region so that we can inform the owner or lender or the party engaging us as to which of the regions they need to be most careful in. There are also the stakeholder curves, ground up loss, direct loss, lender loss, and we can do various different kinds of sub-portfolio analysis. So we can take logical groupings of properties and show the component losses under the total portfolio. We can compute average annual loss or annual expected loss. These are in some way related to the premium that would be required to offset the loss over the long term. And we can deaggregate the average annual loss by earthquake source. So we can see which faults are responsible for what part of the loss to the overall portfolio or any part of the portfolio. And all of these things help to tell us where the losses are coming from and where the owner or lender needs to be most careful. So what are some recommendations we can draw from all of this for best practice? So if we're recommending best practice, if you're the engineering service provider working with a lender, you want to compare models and choose the best model, the model that is best suited to the user's need, and then learn the model. Check the hazards, compare the event set and its hazards to the United States Geological Survey and the National Seismic Hazard Mapping Project. You can run a stripped down single site analysis and compare to good PML. You can ask questions of the CAT model provider and knowledgeable users and make an informed choice of models. Then the next thing is to get a high quality statement of values. That's the values for each of the different properties. It's sometimes called COPE information for construction, occupancy, protection, and exposure. And then check that these values are reasonable, that the replacement costs for different forms of construction make sense. Next, we can sift through past PML reports and use any of the information that we deem reliable and use it in terms of making sure we've got the structural types correct, that we may have some of the secondary modifiers appropriately used, and that we know the site hazards and have executed overrides where we have something that may differ from what is pulled out of the insurance CAT model. We want to focus on the most important sites. In some way, we have to identify those sites by exposure and by clustering around large faults, other means. We want to then gather data and make site visits and review drawings as permitted by the scope, budget, and schedule, and do most of the work on the most important sites, driving the risks that will be large portfolio-wide risks. We want to improve site and building modeling data, the site class and liquefaction susceptibility from soil reports, assign the appropriate structural classes where information is available to support that, and add those secondary modifiers where the information is available. And if we can calibrate to reliable past reports, then that's a desirable thing too. And then if we can save all the data and the building modeling, the site data and the building modeling, and if we're doing this analysis on an annual basis, then we want to save and improve the quality of data through time as we are able to complete more detailed reviews of more and more of the portfolio. So let's see, here's a bibliography and some additional resources for portfolio seismic risk assessment, taken from some of these sources and others. We'll let you read through this on your own time. So quite a variety of different things there, and I'm sure there will be more things that will be listed in the ASTM for portfolios. So what are some questions that would come up as we discuss portfolio seismic risk assessment? One of the things would be, why don't we just examine a single scenario or a few maximum scenarios in each region? And I think we saw how portfolio seismic risk assessment provides a better answer and provides a more complete answer in terms of not only all the levels of loss that can occur, but all the losses that occur to specific stakeholder parties. And why not just use correlation methods with single site loss recurrence relationships? And because of the geographic correlation of loss, we've selected to use an earthquake by earthquake analysis procedure, and that's suited for doing the stakeholder analysis as well. How do I calibrate a damage model in an insurance CAT model to any of the past PML reports and results that I may have? And of course that presents a challenge when we're using the insurance-based catastrophe models, but some of the engineering-related models provide a more direct path for that. Otherwise, we certainly want to make sure we've got the structural types correct and any of the secondary modifiers correct. And then things about what effects do secondary modifiers have, or what's the best catastrophe model to use, and we'll leave it to the individual owners and engineering service providers to have those conversations with the catastrophe model providers. And that concludes the webinar. Thank you very much, and we'll have lots of time to talk about this during the discussions online.